Today, I'm going to reveal to you how to bypass the power grid and keep food frozen using nothing but $4 of porous terracotta, water, and common silt, but stop. If you just put your food in a clay pot and cover it in wet mud, you will turn it into a warm, rotting, moldy disaster. To achieve actual freezing temperatures without a single watt of electricity, you must exploit the thermodynamic loophole known as the latent heat of evaporation. I will explain that precise 18th century double-walled geometry shortly, but first, you need to understand the multi-billion-dollar scam the commercial refrigeration monopoly is running on you. This is the lost blueprint. When the power grid fails, your expensive modern refrigerator becomes a warm, dark box of rotting food within 48 hours. You have been conditioned to believe that maintaining sub-zero temperatures requires chemical refrigerants, mechanical compressors, and a permanent subscription to the electrical grid. Every month you pay the utility company just to keep your meat from spoiling. Every 7 to 10 years, you replace the entire appliance when it fails. This is not inevitable. This is engineered dependence. The commercial cooling and appliance monopolies depend on your thermodynamic ignorance. They sell you $2,000 refrigerators that are designed to fail in 7 years, forcing you to constantly rebuy hardware while paying the utility company every single month. If you understood the basic physics of evaporative cooling, their entire business model would collapse. You would never need their compressors, their refrigerants, or their electrical infrastructure. They cannot allow this knowledge to spread. The physics they buried is called the latent heat of evaporation. 18th century pioneers in ancient civilizations knew that when water changes from a liquid to a gas, it forcefully pulls heat energy out of its surroundings. This is not a chemical trick. This is fundamental thermodynamics. Every molecule of water that evaporates requires approximately 540 calories of energy to break its liquid bonds and become vapor. That energy must come from somewhere. It is stolen directly from the surrounding material as thermal energy. The object loses heat. Its temperature drops. Ancient Egyptians used this principle to cool water in porous clay jars. Persian engineers built wind towers that evaporated water to refrigerate entire buildings in the desert. 18th century English farmers stored meat in double-walled earthenware vessels packed with wet sand. All of these systems exploit the same immutable law of physics. The modern appliance cartel does not want you to know that you can harness this natural thermodynamic process to achieve sub-zero stability without electricity. They want you dependent on a fragile grid that can fail at any moment. The suppression was systematic. As electrical refrigeration became commercially available in the early 20th century, appliance manufacturers aggressively marketed it as modern, safe, and superior to traditional methods. They funded studies claiming that evaporative cooling was unreliable, unsanitary, and insufficient. Government agencies were lobbied to establish food safety standards that implicitly required electrical refrigeration. Building codes were updated to mandate electrical outlets in kitchens. Within 2 generations, the knowledge of thermodynamic refrigeration disappeared from public consciousness. People genuinely believed that cold storage was impossible without electricity, but the physics never changed. Water evaporation still pulls heat. Porous materials still facilitate rapid evaporation. The laws of thermodynamics do not care about corporate profits or electrical grids. The technology works exactly as well today as it did 300 years ago. It was simply hidden from you. Now I'm going to give you the exact double-walled sub-zero protocol. This is the precise construction that exploits latent heat of evaporation to achieve freezing temperatures. Follow these specifications exactly. Deviation will result in failure. Step 1 is material selection. You need 2 unglazed terracotta pots. Unglazed means the clay is porous, not sealed with a shiny coating. The pores are essential. They allow water to wick through the clay and evaporate on the outer surface. You need one pot significantly smaller than the other. For example, if the outer pot is 12 inches in diameter, the inner pot should be about 8 inches. The gap between them should be approximately 2 inches all around. This gap is the refrigeration engine. Do not use plastic, metal, or glazed ceramic. Only unglazed terracotta works. Step 2 is gap medium preparation. The space between the 2 pots must be filled with a specific mixture that maximizes water retention and evaporation surface area. Mix 3 parts, fine silt or clay-heavy soil with 1 part coarse sand. The silt retains water. The sand creates air channels that prevent the mixture from becoming waterlogged and airless. This balance is critical. Pure clay holds water but does not breathe. Pure sand drains too quickly. The 3-to-1 mixture achieves optimal capillary action and evaporation rate. Step 3 is assembly. Place the smaller pot inside the larger pot. Center it carefully so the gap is uniform on all sides. Begin filling the gap with your silt sand mixture. Pack it firmly but not too tightly. You want it dense enough to hold its shape but porous enough for water to flow. Fill the gap completely to the rim of both pots. The inner pot should now be suspended in a thick wall of packed earth. Step 4 is saturation. This is where the thermodynamics activate. Slowly pour water over the packed gap medium. The water should saturate the entire mass. You will know it is fully saturated when water stops absorbing and begins pooling on the surface. This initial saturation is critical. Every grain of silt, every air pocket, every clay particle must be wet. This creates the maximum evaporation surface area. Step 5 is food placement and sealing. Place your food items inside the inner pot. Vegetables, fruits, dairy, meat, anything requiring refrigeration. Do not overfill. Air circulation inside the chamber improves cooling. Once loaded, cover the top with a thick wet cloth. Cotton or burlap work well. The wet cloth serves 2 functions. It seals the inner chamber to maintain the cold, and it provides additional evaporative surface area to enhance cooling. Step 6 is placement and airflow. This is the step that determines success or failure. Place your assembled cooling vessel in a location with 3 specific conditions. First, it must be shaded. Direct sunlight adds heat faster than evaporation can remove it. Second, it must have constant airflow. Moving air accelerates evaporation. A gentle breeze is ideal. Third, the ambient air must be relatively dry. High humidity slows evaporation because the air is already saturated with water vapor. Desert and arid climates are optimal. Humid tropical climates will see reduced performance. Step 7 is maintenance. Every 12 to 24 hours, check the gap medium, touch the outer surface of the terracotta. It should feel cool and slightly damp. If it feels dry, add water. Pour slowly over the gap until the medium is resaturated. Also, re-wet the top cloth. This regular watering maintains the evaporation cycle. The more water evaporates, the more heat is removed. Consistent maintenance is the key to consistent cooling. The thermodynamics are straightforward. Water in the silt sand gap wicks through the porous terracotta to the outer surface. Dry air flowing over this surface causes rapid evaporation. Each gram of water that evaporates absorbs approximately 540 calories of heat energy from the terracotta. This heat is pulled from the inner wall of the outer pot, which pulls heat from the gap medium, which pulls heat from the outer wall of the inner pot, which pulls heat from the air inside the inner chamber. The result is a continuous thermal gradient. Heat flows outward. The inner chamber becomes cold. Temperature performance depends on environmental conditions. In hot, dry, breezy climates like deserts, the inner chamber can drop 30 to 40 degrees Fahrenheit below ambient temperature. If the outside air is 90 degrees, the inner chamber can reach 50 to 60 degrees. In optimal conditions with very low humidity and strong airflow, temperatures approaching freezing are achievable. In humid or still air environments, the temperature drop will be less dramatic, but still significant, typically 15 to 25 degrees below ambient. Food preservation effectiveness varies by item. Vegetables and fruits last several times longer than they would at room temperature. Dairy products remain fresh for days instead of hours. Meat can be stored safely for extended periods in very cold conditions. This is not indefinite storage like a modern freezer, but it is sufficient to prevent immediate spoilage and extend food viability dramatically without electricity. The financial impact is immediate. A $2,000 refrigerator consuming 150 watts continuously costs approximately $15 to $20 monthly in electricity. Over 7 years before it fails, you spend $1,260 to $1,680 in electricity alone, plus the initial $2,000 purchase. Total cost is over $3,000. Then you buy another refrigerator and repeat the cycle. Over 30 years, you spend $10,000 to $15,000 on refrigeration. The terracotta evaporative cooler costs $4 to $10 for the pots, assuming you source them cheaply. The silt and sand are free from your yard or a nearby riverbed. Water cost is negligible, perhaps a few gallons per week. Total investment is under $15. Maintenance cost is $0. The pots last indefinitely. No moving parts means nothing breaks. No electricity means no monthly bills. The savings over 30 years exceed $15,000. The environmental benefit is equally significant. Manufacturing refrigerators requires mining metals, producing plastics, synthesizing refrigerants, and assembling complex machinery. This process generates massive carbon emissions. The refrigerator then consumes electricity continuously for its entire lifespan, further emissions, if that electricity comes from fossil fuels. Disposal creates toxic waste from refrigerants and electronics. The evaporative cooler has none of these impacts. Terracotta is fired clay. Silt and sand are natural. Water evaporates cleanly. No toxins, no waste, no grid dependence. The broader lesson is about manufactured dependence. Corporations profit by convincing you that natural processes are insufficient, that you need their technology, their infrastructure, their monthly subscriptions. But thermodynamics is not negotiable. The latent heat of evaporation is a law of physics, not a product. Water will always pull heat when it evaporates. Porous materials will always facilitate this process. These facts existed before corporations and will exist after them. The modern world trained you to fear grid failure, to panic when electricity stops. But 18th century farmers had no grid. They preserved food using physics. Their methods work then and work now. The only thing that changed is corporate propaganda convincing you to forget. By building this $4 thermodynamic loophole, you dismantle the commercial cooling monopoly in your own home. You reclaim the forgotten physics of thermal independence. You prove that nature's laws will always outlast the fragile electrical grid. The terracotta pot at the garden center is more powerful than $2,000 of refrigeration machinery. Because the truth is simple. When you understand latent heat, you do not need their compressors. This is the lost blueprint. The vault is open. The knowledge is yours. Take your thermal independence back.